This is Humpty Dumpty worksheet part 3. Yeah, it's burning. We made fire and we put it out with sand. So this is 2. We've done these. And we're looking at number 2E from the Humpty Dumpty worksheet. Who thinks he's all that? It says draw rough diagrams DT and VT for throwing up and down. Actually, you guys, everybody stop. You should all watch this and know. So when you throw something up and it goes up and comes back down, what does the DT graph and the VT graph look like? Just tell the person beside you what you think the shape would be.
VT is straight, right? DT is curved.
Definitely, that's good, Izzy. Yeah. Izzy's saying VT is straight and DT is curved. That's true. How do they look? What do they look like? This graph looks like this. It looks like it's motion because as it's going up, when it leaves your hand, it's going quickly up, right? So this, it's steep. And then it goes up. What is it doing right at the top? It's stopped, right? So this is kind of flat at the top. And then of course it comes back down and it gets faster and faster on the way down. Okay, but the VT graph is interesting. Izzy's very excited. Tell me, Izzy.
Okay, wait, I'm probably wrong, but does it go like that?
You might be wrong about that. Think about it though. Tell me why.
Well, because of...
What's the velocity right at the beginning? Izzy went like this, by the way. But it's not like this. Jaya, what do you think?
Oh, I had a question with the DT graph.
Okay, tell me.
Why does the distance go up and then the distance go back down? It's because it's going down?
Yeah.
And it travels like a bigger distance.
Right, so the slope is steep upwards at the beginning because when it leaves your hand, it's going up fast, right? Then as it slows down, stops, and then it comes down slowly and then speeds up as it comes back down. It ends up in the same place where it started.
Okay, so the distance increases and then it decreases because it's going down. Will it always be like that for those kind of
Yeah. What's the velocity when it leaves your hand? Oh, Serena just went like this. Is this right? Seems very simple. Can't be, it's complicated motion up and down. It can't be that simple, no? But it is that simple.
Oh yeah, because when it leaves your hand, it slows down, right?
Good. When it leaves your hand, it's going upwards fast. High velocity, positive. And then it gets slower, 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 slower. What happens right here? That's when it's stopped at the top. And then it starts to come down. So downward is negative velocity, right? And of course it gets faster and faster and faster at the bottom. What would the slope of this line be? You know the number. How is the velocity changing every second? You should all know the answer to this question. I'm going to put it on your test now. Jessica. Very good. Excellent. You're on fire today. Yeah. Acceleration of gravity, right? So the rate of change of velocity is the acceleration of gravity. It's this slope. And that's why it's straight, because gravity is constant. That's 2E. And now I'm going to do 3.
Wait, what about the AT?
You want to do the AT?
Yes.
The AT would look like, tell me what it would look like.
A flat line. Flat line.
Yep, at what value?
0.
Nope.
No, negative 9.
This would be negative 9. Why does this acceleration not change?
Because it accelerates in the hand, not my feet.
When it's in the air, it's accelerating at a constant rate because of what force? Gravity. Gravity's constant. So this just stays the same the whole time. Good question, Izzy. Thank you. What's this? My boards are getting messy. Now I'm going to do number 3, D, and E. So Ryan Miller used to be a goalie for the Vancouver Canucks. That's why he's in here. He wasn't very good. He throws off his mask in fury over letting in a goal. And he throws it straight down. So he's on a cliff. And he's like, I've had enough. And here's his goalie mask. And he's going to throw it downward. So his VI is downward 25 meters per second. And the cliff is 100 meters high. And we're asking, oh, this is the sound one. This is crazy, okay. So the speed of sound, the question asks, like, at what velocity does the mask hit the ground? So you're looking for VF. And then it says how much time passes between throw and impact, so you search for time. And then where is the mask when it's falling at 40 meters per second? So you make VF equals to 40 and you solve for D. And then letter D says sound travels at 335, which is pretty close to the real value. And sound's not affected by gravity. It doesn't accelerate. It's always the same speed. It only is determined by the air that it's moving through. Okay.
What's a Danny?
So from the instant he throws it down, why does it say Danny Boy there?
Yeah, who is that?
Oh, I think I changed this question.
Wait, so is it the
I was
person
mad at
standing
Ryan
up?
Miller. It used to be Danny Boy, and I changed it to Ryan Miller, and the Danny Boy got left over there.
So it's
So
still
it's
Ryan.
just Ryan Miller.
Okay.
Yeah. How long is it till he hears the sound? So we need to find two things.
When it hits the floor and when the sounds come
Yes, we need to find the time of the drop. So we need the time of the drop on the way down, and then we need the time of the sound to make its way back up to him. So let's do the time of the drop first. So this is going to be accelerated motion, and our VI is going to be, should we make down negative or positive? You people are positive people. Okay, so VI is 25, and we know D is equal to 100, and A is 9.8, and we're gonna look for T. This is probably for most of you gonna be a two-step process, because if you use the third formula, you're gonna have to use a quadratic formula to find time. Some of you can do that. If you're not, you're gonna go whoop, and you're gonna go first, find VF. You probably would have found it already in the question, but let's just do it anyways. So we're gonna use the second formula, and we're going to solve this for VF. So we're gonna do the square root of 25 squared plus 2 times 9.8 times 100. And that's going to be 625 and 2,000. So 2625. That's ugly. 625 plus 2 times 9.8 times 100. Looks like 51. 50.8. Is my VF. It's positive because we made down positive, but it's still downward. Okay, that's my VF. And then the next part of this, finding the time, we just use our first formula now. So this was just finding VF. And now we're gonna find T. So we use our first formula. And we're gonna solve it for T, so we're gonna do VF minus VI over 8. And that's gonna equal T, and that's gonna be this number. And if you leave it in your calculator, you can just go minus 25 equals and divide by 9.8. And you're gonna get 2.64 or so. So that's the time of the drop. And then we have to add it to the time the sound takes to get back up. Now the sound's not accelerating. So we can just use V equals D over T. And of course you put the T up and the V down. And you're gonna have D over V. So that's 100 meters over this speed. And that's gonna be, oops, 0.3, I'll say 0.299 seconds. And so if you add them together, this is the time of the sound. And then you add this and this together, and it's going to be about 2.94. So the fall is accelerated, the sound is not. Use the simple time formula to find time of the sound. Oh, and we can just draw the graphs and then we'll be done. So the graphs of this will be similar to this, but not with this part. Yeah, just let me do the graphs here quickly. So for something falling, it's going to be going down to begin with, not flat, because he releases it moving, and it's just going to curve like that. And this one is going to be like this. It's going to start at a negative velocity and get more and more negative. And that's all. So I'll post these videos on the classroom, and you guys can look at them later.